All right, so in this problem, we've got iodine 131, which that doesn't matter, but it's just some element that we have. And we have 200 milligrams of it, and it has a half-life of 8 days. And then I'm going to answer 3 questions here. One question is going to be to write an equation, or let's just say I'm going to find the model. Find the model. Now, for this class, the model must be in this form. There are other forms which are appropriate and which are correct, but for this class, I'm requiring you to use this model. So I want to find the model in that form, and I guess I'll just take these one at a time and just start there. So finding the model in that form, I want to take this information and just recontextualize it and say that what this means to me, contextualized in a table of values. So this is telling me that at time 0, I have 200. And then with a half-life of 8 days, that means that at time 8, I've got 100. And I'm going to use these 2 points to find the model, just the way I would use 2 points to find the equation of a line in the form y equals mx plus b. And I'd look for m and I'd look for b. In this case, I'm going to use 2 points to find this exponential model in the form a e to the bt, and I'm going to find a and find b the way that I would find m and b in a linear model. So I'm going to take the first point, 0, 200, and I'm just going to plug that in. So that means that a is 200, lowercase a, e to the b times 0. And then looking at this, b times 0 is 0, and then e to the 0 is 1, and a times 1 is a. So all of this is to say that a is equal to 200. Now, after you've done a few of these, you begin to see that, oh, this is always working out this way. That given that point, 0, and then some value, that's what a is equal to in the exponential model. So we've got a, and I can write a equals 200 e to the bt, but I need to find b. So I'm going to take the second point, 8, 100. I'm going to plug that in. 100 equals the lowercase a, which is 200, e to the b times, and then in this case I know that t is 8. And then I need to solve this for b. At this point, that's what I'm looking for. I'm looking for that b. So solving this for b, I'm going to say 1/2 is equal to e to the 8b, and then I will say that ln of 1/2 is equal to 8b using my definition of a logarithm. And then finally, there's a number of ways that I could go with this. I could say I've got ln 1/2 over 8. I could say I've got 1/8 ln 1/2. And then I could also say that I've got ln of 1/2 to the 1/8, which that's a little difficult to read what I'm saying there, but I'm using the power property, right? And so I could write it like that, which actually might be the nicest way to write it for the model. But I think I'm going to go with the top one. Okay, so I'm just going to fill that in for b up here, and then that's my answer to the first question. It's the model is 200 e to the, I'm going to do it like this, 1/8 ln 1/2 times t. Okay? Now, one thing to recognize in this is that this is, I've got two factors here, actually 3 factors, but I can split it up into 2 factors and say I've got this factor, 1/8 ln 1/2, which is just some value, right? and then I multiply that by t. Well, according to the laws of exponents, I could rewrite that as a power to a power. So I could say I got e 1/8 ln 1/2, and then say that is raised to the t. That's important to remember, so that's all this means, right? Because when I have a power to a power, I multiply. So these are equivalent to say the power to a power is equal to the product of those two factors. I think that's useful because now I can see. So first of all, this is the answer to the question. And remember, this is not the most efficient way to say this. I'm not saying that it's the best way to say it, particularly now. There is a more efficient way to say this now. But for calculus, we want the e, because you will find that e to a power in calculus is a very convenient form for this to be in. In this case, however, look at what I could simplify this to. But again, I want to reiterate, you have to show me this, okay? Now, after showing me that, if you want to simplify it in this way, remember that a to the log base a of x is equal to, think about it, it's equal to x. That should be in your list of properties of logarithms. So if you look at that and then look at this, I've got a base, and then I've got a common base here. ln is log base e. So that's like my a to the log base a. I've got e to the log base e. And then, so I can use that property of logarithms to rewrite this. And remember that, and also remember that the power property is going to put this 1/8 up as the exponent. So I'm gonna skip a step here because I'm kind of running out of space, but hopefully you can follow it, that I can say that this is 200 1/2 to the 1/8 to the t, which I could write, because it's power to a power, I could just multiply by t, all right? And then, like, more likely, I would say that this is 200 times 1/2 and then to the t over 8. All right? So that would be the first question that I would ask about this. Now, the second question that I would ask is something like, how many grams are left after, so I might say after 17 days, how many grams are left? Well, now I've got the model, and not only do I have the model, I have the simplified model. So I can just say that a of 17 is equal to 200 times 1/2 to the a over 17. And then that's just a calculator entry, which I'm not even going to do. I'll leave that for you, but we would get a decimal approximation. That's simple. Once we have the model, we just plug in for the t, and we've got it. But the other question that I might be asked is, I could say, how many days until 10 grams are left? All right. Now this is slightly trickier. So using the model, and remember that the model is a equals, and we've got the 200 times 1/2 to the t over, did I do that wrong over here? I did that wrong. It should be, this should be, I flipped it upside down. This should be 17 over 8. Okay, so it's t over 8. So this will be 17 over 8. All right, and the model is t over 8. All right, so there's the model there. That's what we had on the previous page. All right, so using that model, 10 grams goes on the left. And then I've got the model saying 200 times 1/2 to the t over 8. And I want to solve for t. So let's divide by 200, and we get 1/20th. And then now we've got that. What thrust us into the discussion of logarithms in the first place was a variable exponent. So this is where we want to use logarithms to solve this. I could do this and convert this using the definition of a logarithm, right? I could say log base 1/2 of 1 over 20 is equal to t over 8. See that? And then to get t, I simply multiply by 8. And that is a calculator entry that I would use to get t from there. Of course, if you have a scientific calculator, you're going to have to use change of base and call it 8 times log, or we could use natural log or log. Natural log of 1 over 20 over natural log of 1/2, and that's what your t is going to be. I believe that comes out to 34.6, if memory serves me right. Okay, so that is how we can address a half-life problem, and then we have the 3 parts to it. One is find the model in my form, a times e to the b x, or t, as the case may be, and then we have, given a number of days, then how much is left, and then we have, given an amount left, how many days does it take? So those are the 3 things that could be asked, and you should be able to do all 3 of those.